Okay, so I think we're going into the kernel trick. Is that? Yeah, okay. So kernel trick, I'm gonna kind of go into some detail here that part of it is also not really in the curriculum. For example, I'm gonna focus a lot of radial basis functions, RBFs. But I think those are kind of a useful thing because they're so commonly used in support vector machines. It'd be really nice to have. But I'll mention about the kernel trick. So this actually works really well with my course when I talk about PCA next, which is what section 37 is. I'll talk about basically how you can do dimensionality reduction. And the kernel trick kind of plays a little bit into this, is that the idea here is kind of the opposite of dimensionality reduction. So you can kind of think of it as saying like putting things in higher dimensions allows us to essentially have things more separable. So it turns out, I won't go into the full thing. I usually talk about like higher dimensional like spheres, for example, turn out to be like they call them like spiky. But the main thing is the idea is that if you raise data into a higher dimension, and by dimension I mean an extra direction, it tends to be easier to make linear separable cuts. So a really simple demonstration I can show of this is if I draw out on like a single straight line, so a one-dimensional line, right? And I have 2 points that are either, let's say yellow, like this, and let's say red. Okay, so you can see here, there's 2 yellows and 1 red. And I say, okay, go ahead and draw a single straight line to separate these 2 out. And then you say to me, Victor, it's impossible, you can't do that. And you're like, yep, you're absolutely right. You cannot draw a single straight line, right, that separates these 2. I can't draw anything that's going to separate yellow from red. It's always going to have some, misclassification, right? No matter what kind of straight line I can have. And then you say, well, okay, well, what if we like didn't draw a straight line? What if we like drew like something like this, or like, we do something a little more generic where we say, okay, if you're between these 2 lines, you'd be fine. You're like, yeah, you could definitely do that, right? It kind of breaks my rule, but you can do that, right? And it would separate, say, oh, and now we have anything between these 2 2 green lines is red, and then everything outside is yellow. Another way you can think about this, turns out, is like, well, okay, what if we raise this into another dimension? And by a dimension, I mean a direction. So essentially, instead of saying, okay, we only have left and right here, we also have up and down. And so let's just give these points just to make it kind of like tangible in mathematics. Let's say this point's at point 0, this is at point 1, and this is at point -1. If I say, okay, let's move everything, and this is x, let's move everything into an x squared direction. Well, that means x squared is going to give us, this point's going to give us 1, this point's going to give us 1, and this 0 point here is going to give us 0. Okay, so, sorry, my phone's going off. I don't know why it's going. Anyway, you can see it's like, okay, then we can raise these points essentially up to that level. So we can say, okay, this is going to move up 1. So now our yellow points are going to look like this. And just pretend those, we'll go ahead and erase these guys. You can see now it's like, okay, now we can definitely draw a single straight line right through here. Oops, using eraser. There we go. And now we can definitely separate them. So that's another way we could do it. It's like, okay, like we could either have found like a more complex, way of separating these points in one dimension, or we can raise it into higher dimensions and then find a more simple once cut, way to do this. So it turns out what's really cool about the kernel trick is that these are actually equivalent to each other. It turns out if you think of it raising to a higher dimension or think about more complicated cuts, they're actually 2 sides of the same coin. Oops, knocked over my water. So that's what makes it like really, really useful to actually play around with this. And this is where usually people say, they usually say like, well, why don't I just do one or the other? And it turns out that sometimes it's really difficult to figure out, like, if you remember back to like linear regression, is that that's essentially what interacting and polynomial features are doing, is that we can essentially build like this more complicated part. That's sometimes really hard to build up like from scratch. Like you have to know what you're looking for to begin with, versus saying, hey, if we raise everything into a higher dimension, we're basically putting it more complexity in the dimensions, but it means we can use something relatively simple like a support vector machine to make that linear cut. and say, hey, that's going to be how we can figure things out. So it turns out this tends to actually be a really useful trick. Okay, does that make sense to people? Okay. So, all right. So again, like I was saying, one thing you can do, like if you have like, let's say start off with two variables, you can then basically combine them in different ways. So you can see here like x, there's just y, there's x squared, there's x times y, and there's y squared. It just allows you more flexibility, more things to play around with. And this allows us then to create these new cuts, and that is what the kernel trick is. Okay, cool. Everyone follow me on that? Okay, I see some head nods. I think overall understanding. Cool. So this is where we can actually say, like, how do we define this kernel? Like, how do we define what thing to extend it out with? So like, for example, I should like, oh, let's square it. If I knew the right thing, I could square it. It turns out there's things like, we can talk about polynomial kernels, which are basically this guy, basically building up different polynomials by multiplying the, what's it called? The features, you know, just the single feature, the feature squared, the feature times the other feature, that'd be a polynomial kernel. There's another kernel called the Rbf kernel. So radial basis function. So I think I should, whatever, that's fine. The radial basis function basically allows us to create this function that we can guarantee to make something into a separable spot, which is kind of a really cool idea. It's like, hey, we can actually design this function. So the way this works, and I'm going to go into some detail that basically, I don't think, has everyone gone through section 36 by chance? I don't. Okay, I see some handshakes. That's okay. But I don't think the curriculum actually talks about RBF very much. It is an option on Scikit-Learn, but it turns out it's a really powerful option. So I'm going to go in some detail here. But the motivation basically is that, like, hey, we start off with these 2 points. Let's say this blue point and this red point here. And what the Rbf function is, so just like kind of we have like before I showed you like the parabola, it's like if we raise it up in x squared, essentially this Rbf, we center it at each data point. And we say, okay, imagine now instead we raise, or in some cases we actually put it in the negative direction. But we basically raise these data points into this spot right here based on this function. And it turns out it's always going to be centered at a specific data point. In this red one, you can imagine going up in this direction here. It's always going to be centered at that data point. And what's cool is that we can actually combine radial basis functions together. So what we'll see is that if we have multiple, let's say, blue points, we can actually combine them together to make one super, you know, Rbf function. And that will basically become the function that we care about, and we can actually separate this. What's really cool too is that we can actually, this red point, I said raising up here, I really should have drawn it like this, is that we can move the red point in this radial basis function right here. And that way we can always separate them. Okay, but you can technically just draw it like this too. So I just kind of, you just multiply by -1 and drop it down. So basically this allows us to always map the points into a spot, so we can basically make one clean cut. So I have a couple other kind of drawings here that kind of show this example. Does everyone understand like this part, like saying we can design this some weird function called an Rbf and these dashed lines and then raise those into those points? Okay, so
Victor, one question. So is this usually for like two classes only, or can we have multiple classes and then separate them?
Yeah, you can have multiple classes. Yeah, so you can have, what's going to happen is that we're going to adjust, we can adjust the Rbf to find a better separation. And what's kind of cool about that is that that's part of the gradient descent too, is that it's going to find what's the best Rbf, like what are the different parameters for the Rbf function to basically separate them out. Okay, so yeah, so just quickly, you can see if adding more points. So you can see here, you can imagine this is the overall function here. And you can see here is that I have this blue one, and this red one. And the idea here is that if there are two peaks that are close together, they get bounced up. If they're opposite of each other, they actually get negative. So this one, I kind of made it as one big part. But I think later on I show you with 5 data points. I'm trying to see if this works. Where did I put this? Nope, I didn't put there. Okay, what this would look like, it'd be looking something like the overall function, which will just be, let's say in black here. We'll have the individual Rbfs look like this. Look like this. And these aren't like really what they look like, but they're close enough. Like this. And so what I'm going to say is like, okay, everything that is red, just multiply it by -1. So what's going to happen, they're just going to be flipped over. And then I'm going to combine them together. So let me go ahead and erase this guy. And so what I can do now is actually combine them together into one part. And I'll just draw this in purple. And it'll look kind of like, oops, it'll look kind of like this. And then this gets subtracted down. So you can kind of see that purple part is basically allows me to say, okay, this is going to be the function. And wherever you are on this function, if you're right here, you're going to end up right here. Does that make sense? And so this way it allows you to say, okay, like this is our training data. And then say, okay, let's say we try to do validation. This is going to raise it up in this area. And that's how we do our separation. So it's kind of nice that we can actually use this now to make a more complicated part by using one base function here. So that's using the Rbf kernel. And so what this looks like in 2 dimensions, so this is only 1 dimension, is that kind of saw a little quick sneak peek here, is this is the original data, x1, x2. And essentially what I like to think about it is like if you have like a sheet, like a blanket, and what you do is essentially you take your hand and you go ahead, pinch the parts, like you pinch at every single data point and you either pull it up or pull it downward, right? So you can see on the red points, I'm pulling them up essentially. And so the more red points that are centered here, I'll pull up even higher. And then this right here is the linear separator, essentially would be what the support vector machine eventually finds, and we'll separate those two out. And note that this linear separator, if I were to map this back down to 1 or 2 dimensions, what this would look like, it'd be something like a little circle that would go kind of like around like this. Okay. Does everyone see that? Okay. So again, this is where I kind of like to imagine like you're picking up like these little like points and moving them up. That's what the Rbf is doing. And then you basically take scissors essentially, and that's your linear separation that's going to cut through. So what's kind of cool is like if you also have a red point right here, you can have the Rbf actually, I'm not going to be a great drawer, but like you can imagine this kind of hill coming up like here. And so you might have an Rbf, you know, from 2 dimensions where you're basically pulling up these 2 different parts and it cuts across. So you actually will see something like a little circle that comes out right over here for like another red point. Okay. Does that make sense? Okay, thumbs up if that sounds good. Sideways, you're like, I don't know. Thumbs down, you're like, this way. Okay, so I see maybe some reluctant, like I see sideways. I see a Meg over there, like, I don't know. So is it that pulling it up is like, is it the process of like saying, oh, like how do you determine this, or is it saying how is this useful? Like, what do you think is kind of holding you up right now? If you don't mind me asking.
So Victor, this might be like a very basic question, but on the graph to the right, you have the XYZ plane, right? Okay, cool. Yeah.
Yeah, and you'll see, for example, it's technically the X1, X2 Z plane, right? So these are X1,
okay,
and this is, sorry, this is X2, and this is X1 here.
And then in the formula that you have right there, I see, I just, how many X is one variable, Y, and B is another variable?
Right, so this X right here is actually a vector. So this is actually going to take in, if I were to draw that out, it'd be like X1, X2 in the matrix here. And that's why you see, for example, that T is standing for transpose.
Okay.
So it can then multiply by W1, W2, which is the W matrix.
Okay.
So that what this would look like if I didn't have this. This isn't my grid drawing, by the way. But this is representing basically that radius basis function. What this looks like essentially is saying, okay, we have this, well, I'll ignore this part, but basically it's like x1 times w1 plus x2 times w2, and then plus just b. Okay, that makes sense.
And in this case, it's only looking at 2 features, but it could be looking at 10, 20, 30 features, and you would have this same kind of separation happening with each of the feature sets.
That's right. Yeah, you would somehow multi-dimensionally pull it in different directions, if that makes sense. Which is, I know it's like that, like breaks your mind. Like I'm like, I don't even know what that's supposed to look like. But hopefully that scenario with like saying from 1D and then like to 2D, that's usually how you'll see a lot of this like analogy done. It's like, hey, let's look at it in 2D. It's like, oh, you see how we do in 2D? Now pretend we can somehow do that in 3D. And that's kind of like what's going on mathematically.
Okay.
Cool.
Thanks.
No problem. All right. So this is where we say, okay, like you can imagine pulling up on these parts, like at least for 2D, right? You kind of pull them up and how we pull it. And then the question says like, well, how far up do we pull it? Like, do we pull it up as a little bit? Do we pull it up a lot? Like, how do we know? And this is where this hyperparameter called gamma. So this kind of looks like a little y here. I don't know if you guys have seen this part, it's gamma. And this hyperparameter allows us to basically say, do we pull up really hard or do we just pull up a little bit? So what ends up happening is you basically having on very high gamma is essentially what we'll get is for very high gamma, we'll get very narrow, which means like we're pulling up really hard on that point. So we'll get like these huge peaks. And if you had a very small gamma, so this is like a very high gamma. And then if you have very small gamma, you would have something more like a gentle slope. Essentially, you're kind of pulling it up and it's kind of got a little weight to it. So you get more of these narrow peaks, which when you cut these then, what this will look like, and pretend this is like 2D, I can't draw 2D, so pretend that's kind of like a 2D mountain, right? Or a 2D hill. What these will look like when we go ahead and put these back into something like this, it'll look like either these like really sharp circles around the data points. So like I'm gonna draw it like this, like it'll be like sharp data point, like circles like this. Or if you had it on small gamma, they'd look more kind of like these gentle kind of curves. So they're a lot less sharp versus when it's very large gamma, you'll tend to see like very small circles that are very close to data points because they're being pulled up really high and then being cut. So hopefully that kind of makes it a lot narrower. Okay. Does that make sense? Okay, so this is a hyperparameter we can adjust essentially to say, do we overfit or underfit? So if you see your thing is underfitting or overfitting, you might want to adjust your gamma to be a smaller gamma and then say, okay, like we've been overfitting, let's relax a little bit on this border. And so this is where I go ahead and show a little bit on the Scikit-Learn example. So this is actually from Scikit-Learn, so they actually talk about this directly on the documentation. So this is a whole thing they talk about, basically what I was saying before. And we're going to reproduce this graph here. And there's actually code that you can go ahead and show and run this. So I went ahead and ran that code here. And so note that I'm using the iris data here. And you'll see here is that basically we're going to use different sets of gamma and different C. So note that basically we're going to adjust those hyperparameters that we talked about, C for support vector machines and gamma for this Rbf kernel, which will be in support of support vector machines. Okay. This essentially, have you guys learned about grid search already? I see a little, okay. Grid search, remember, allows us to basically try out a whole bunch of hyperparameters at once. And so we're basically trying out, when we see, for example, well, in this case, log space, but basically 10 to the power of -2, 10 to the power of 10, 10 to the power of 13. Essentially what that's going to say is like, okay, we're going to have essentially 3 different parameters and then 3 different parameters and then all the different combinations you can have. So it'd be like essentially 6 or 9 different combinations we can have in total. So that's what this grid search is doing. So actually what those overall effects are, I think I already ran it, is this guy right here. And this is where I'm going to open the image in a new tab just so we can kind of see it a little better. Okay, so the problem is I have a dark screen in the back, so you can't see the numbers. We'll see. Oh, this is close enough. We'll use the one from Scikit-Learn's documentation. So you can see here is that basically each of these plots is a different support vector machine that was trained on this data. So note that there's blue and there's red. You guys can see that okay, right? The difference between that blue and red. And so the whole goal is to find where blue and red is. So you can see here when we have very, a very small gamma, so 0.1, 10 to the -1, and then a very small c here, 10 to the -2. Basically, our c said, how much do we care about our classification? In this case, we don't really care that. Basically, this small c saying, we don't really care that much about classification. And you can see this very simple line right here, is that it's like, well, technically it's getting like most of these blue on the left side and most of these red on the right side, but it's too simple, right? It's underfitting in this case. So one way we can adjust for underfitting is that we need more complexity. So one thing we can do is basically turning up C, say, hey, we do care about classification more. So you can see if I move downward here, C goes from 10 to the -2, so 0.001. This is just 1, and this would be 100. And you can see here is that we actually, especially on this 100 part, you can see it's caring a lot more about classification, and it's trying to separate these out. Note that gamma is still really low, so we're only pulling on that like imagine like I'm kind of pulling on it very gently on the like the napkin, like, you know, or the sheet, like basically pulling it very gently. So there's a lot of crossover here. So if we notice from like right here and move on to the right here, we actually increase gamma. So gamma started with 0.1, gamma to 1, and then gamma to 10. And you can see as we move up here, you can start seeing it's starting to fit really well. And this part right here, I would probably say this is starting to look like it's overfitting. And you can see there's kind of like, it's classifying each individual part really, really well. However, you can see that the points are just really close together, and that's because we're pulling really hard on those points with a high gamma. You can see the extreme basically of a very high C and a very high gamma. It basically at this point is just saying wherever the points are specifically is where it is, so it's not going to generalize very well. And so this is probably like the happy mediums over here. And I'd say probably this one to maybe like, I don't know. I think this one looks just pretty good right here, is that it still makes some mistakes, but you can see like it's getting the overall shape. You can see there's kind of this extra curve going through here. It's still making these mistakes like these blue ones here. So maybe if there's a more, you know, like we need to have this part, maybe it makes sense for us to have something like this, or even like something down here. Okay, so that's kind of the idea of like adjusting these different parameters in here and how they interact. Note that if you didn't know about like it pulling up, you can also think of gamma as being, are they going to be very small circles or more wider circles? So you can kind of see a little bit as gamma is smaller, the overall kind of like encompassing circles around the points tend to be a lot larger. As we get larger gamma, we get very small, narrow circles. Okay. So, and you can see here in this case, Scikit-Learn, that code up there actually tried out many different parameters, many parameters of C, many parameters of gamma, and the white basically saying it's validation accuracy. So this is data that it hadn't seen from not the training data, basically saying, well, let's put the validation and see how well it performs. And it looks like for C, like, you know, for 1 and gamma 0.1, which I think is this one right here. No, 1 and 0.1. This one right here. Is that right? Gamma 0.1, 1. Yeah, so this right here actually does pretty well on the validation set, which you might say, oh, it doesn't look like it does very well here, but that's because we didn't see the validation set. We're seeing the training set on here. So that's why, for example, this set right over here, which looks like it does really, really well with high gamma, let's say a gamma of 10, which I think is right here, and a C of 100. Let's say right here, you can see that that's not doing the best job. It's getting around like maybe 0.7, maybe even lower than that. And you can see basically that it's overfitting. Okay, so this is an interesting way for them to kind of represent, but you can kind of see essentially is that there tends to be a little bit of like a hot spot essentially. It's like, oh, this is where you should be. But note that there's also, in this case, looks like it does a pretty decent job on at least the validation set if you're having high C but low gamma. So note that grid search allows you to kind of adjust these parameters. There are only 2 hyperparameters in this case, but allows you to adjust those hyperparameters to try to fit in as best as possible into that global minimum, basically the least amount of loss or the highest accuracy, right? But there might be multiple ways to get there. So you can see here, for example, high C and low gamma does probably about the same goodness as this kind of hyperparameter tune. I would probably say if I had to choose between these 2 different models, I would prefer these kind of models because this tends to do, this seems more reasonable versus like, why do I have to turn up C so high? Why do I have to care about classification so high and turn gamma so low? It seems like I'm kind of counteracting each other where I want something a little more balanced, which makes a little more sense. I'm trying to think of anything else I should mention about this, but yeah, any questions? No? Sound pretty good then? Yeah, okay. So this is, as you guys get into grid search, and you can see why it's called grid search, because you're essentially searching on a grid of like what the hyperparameter is going to be. So we saw there were basically 3 different choices, and basically 9 possible models. Note that when you do a grid search, any grid search, you have to train each one of these individually. So grid search can take a long time if you have it go through a whole bunch of things. You want to be careful of that you don't just put down every single possibility in your grid search, because then it's going to train every single possible model, which might be literally hundreds of models if your grid search is large enough. And one thing to note too is that support vector machines tend to train slower when we care higher and higher about the classification on here. So certain values of hyperparameters can actually make the parameter, the training slower too. So this is something that's useful to kind of play around with when you're first learning about how these machine learning algorithms work. Okay, cool. Yeah, so any overall questions then about support vector machines or anything else we talked about? Yeah, sound pretty good. All right, so I'll go ahead and stop recording here then.